So I'm going to send it over to Mark. He is a wonderful previous middle school teacher. I'll let him introduce himself. But you're going to learn so much, and I'm so excited that you get to hear from him today about all the really great things that we have for middle school students.
All right. Well, thank you, Kara. And I am going to share my screen quickly. I saw a question in the chat. Couldn't find redeem. So if you go, let's see, right up here, here's our website. Right up here in the upper right-hand corner, it says redeem code. Oops. Um, Sorry about that. And then you just click on that redeem code, and it'll ask you um, for a code and for the code, and then the just an email address. Um, Nothing else. So, welcome everybody. Thank you for the introduction, Kara, and thank you everybody for attending. Like Kara said, I'm a former middle school math teacher from '87 to 2001, so a while ago. Since then, I've been in product development and content development for either major publishers or supplemental publishers. But and I have now been Brainingcamp about 4 years. And as we go on, I'll tell you a little bit more about how I used manipulatives and what they did for me. But I want to start out with just a little bit of an agenda tonight. We'll take a look at why we would want to teach with manipulatives. We'll take a look at a few specific models or manipulatives like two-color counters, Cuisenaire rods. If you're not familiar with Cuisenaire rods, hopefully you'll be excited about them by the end of the webinar. We'll look at color tiles, and then like I was telling Kara before we started, I want to get to algebra tiles, so I may cut a few things short so that I can get to algebra tiles. And every time I open the chat, it opens full screen for me here. Now, if you can see on the slide, and I'll put this in the chat, I have created a Google folder with some resources for you. I just put that in the chat, and in there you'll find some directions on how to create share codes, and then a handout which will have all the share codes that I'm sharing with you tonight. So you'll have those to use as you see fit. All right, let me go back to the PowerPoint. There we go. All right. I thought I'd start off with a quote, or I should say a definition from Albert Einstein about the meaning of insanity. And this was me when I was in the classroom with my eighth graders. Most of my career was spent with eighth graders. I was doing the same thing over and over again, and expecting different results, and having the same, I'll say, conversation with the same handful of kids just about every day. And after about, I want to say my third or fourth year of teaching, I realized that something had to change. And I realized it had to be me. And so that's when I started to, that's when I began to use manipulatives with my middle schoolers, with my eighth graders. And I will tell you, the use of manipulatives, now at that time it was hands-on manipulatives, physical manipulatives, really transformed the way I taught and transformed how my kids learned, and what they expected, and what they how they owned the learning. Quick story with the eighth grade students, we were doing some work with color tiles and square roots. And we were building squares and talking about the idea of perfect squares and what are the dimensions and how could you find the total number of squares. And we started to talk about how the word root in mathematics means the answer. So the term square root um, kind of evolved into, oh, if I could make a square out of these color tiles, then it's a perfect square. If I can't, then it lies somewhere in between these two numbers or squares that I can make. And afterwards, I was standing at the door saying goodbye to everybody, and one of my students came up and she said something to, and I'm paraphrasing, something to the effect of, so if I can make a square or envision a square or draw a square, then I know that number is a square root, but if not, I can determine which two it's in between. And I said, exactly. And she stopped her foot and said, why didn't you just tell us that at the beginning? So they were used to just being told. And so manipulatives really helped them become more active learners and more involved. And it really helped me become more of a facilitator of the learning rather than just a sage on the stage. Uh, yes, the Google folder will be available um, for forever. So yeah, it'll be available later as well. Um, all right. So in 2013, NCSM put out a position statement about the use of manipulatives, whether it's concrete and or virtual manipulatives at all grade levels. And they then went on to talk about, well, how does this get accomplished? How do we accomplish this? Well, we accomplish this by making sure that folks understand that they're not toys, but they are powerful learning tools that we can use to help build understanding, conceptual understanding of math topics. I have read research where a lot of teachers in this research study were using them as kind of a reward system, or hey, today is like a fun day, so we're going to use manipulatives. So again, recognizing that these are really, really strong learning tools that we should be using with kids at all grade levels. So the idea of manipulatives, so I got to tell you, at first when I started using manipulatives, I was kind of thinking, well, I don't want them to become dependent on the manipulatives. And, I'm sure if you have kids or nieces and nephews or grandkids, that you probably taught your kids how to ride a bike and had training wheels on there, or you taught your kids to drive and, you were in the car while they were driving, as nerve-wracking as that may have been. Um, but I'm sure your goal was not that those supports, those scaffolds, those tools, the training wheels, or you yourself holding up your son or daughter as they work on balancing, right? Or being in the car when they drove all the time. Um, I'm sure your goal was to get rid of those and you didn't want to have to be there or take those you wanted to take those training wheels off. And that's how I see manipulatives. They're those things, those tools that help kids learn the math. I don't want them to do the math with the manipulatives. I want them to learn the math with the manipulatives because really our goal is to get them to the abstract and get them working with symbols and um, not being reliant on the manipulatives, um, but being able to operate in the abstract. Now, I don't know if any of you have read this book, Principles to Action from NCTM. I think it was published 2014. They're now celebrating the 10-year anniversary. Um, I think it's one of the better books published by NCTM. Um, if you've read it, let me maybe post in the chat that you've read it and maybe how you liked it. But I thought it was I think it's one of the uh, better publications they have. But in that, they talk about effective teaching practice for math and the idea of using and connecting multiple representations. And within principles to actions, we see this model that you see on the screen that we often see in some form or another when we're talking about manipulatives. And that is that CRA, that working with manipulatives, I'm going to say manipulatives and models, the concrete, and then where they create their representation or that visual representation. Then we want to get them to that symbolic representation. And ideally, kids could move within and among these five different representations, mathematical representations. I kind of look at it as like, well, this is how we do math, right? We see it, we build it, we use the symbols, we talk, we describe it, we have a context that makes sense to us, and when we're incorporating all these, that's when the real learning takes place. And I like I said, I like to think of this is kind of how we do math. So we'll take a look at some context today or this evening or this morning. Sorry. Um, so I thought we'd start with um, integers. And so in talking about integers and working with integers, there are two different models. We'll probably spend most of the time tonight with the counter model, as you see over here on the lower right hand side. But there's two aspects, two concepts, I'll say two facets of these of each of these models, and one, and we're talking about the counters. That's the the, the number of counters, or if we're talking about quantity, or I might say magnitude, if we're talking about the linear model, then it's that length of that directional arrow. Because now our integers, now we have direction. And then one of the other concepts is the idea of opposites, right? Additive inverse. In the counter model, it's different colors and they have a plus and a minus, but in the number line model, they are different directions. All right, so I am going to get started. Now, hopefully you are, sorry, the chat keeps opening full screen whenever all right, so let's take a look at using the number line. Now, I'm going to put this share code in the chat. So if you're logged in, you have the opportunity to follow along. And I'm going to put that share code right up here in that share code box. And we'll take a look at using this linear model. Starts off with a question. And you know, integers seems to be like one of those concepts that we seem to focus on the concept first without context, right? We tend to take a look at these new numbers, new types of numbers, or I should say new subset of numbers, new set of numbers, subset of the real numbers. So how can we model integer addition on the number line? Well, let's take a look at that first example. And I'm going to use these tools over here. We've got 12 plus negative 10. So I'm going to call it a vector. And I'm going to place it up there. I'm just going to stretch it out to represent or have a length of 12. And then from that, I'm going to take the red vector, which is going in the opposite direction, and I'm going to start it where 12 ends. And now I can identify that sum. I'm going to take this marker out here. I can drop it there, and I can see that I get a sum of 2. Now, when you look at those two vectors, what might you notice about those two vectors? What is that length of each of those vectors representing? Yep, one shorter. All right. Now, distance from 0. All right. What do we call that distance from 0? Think about like when we talk about the process of adding integers. Yeah, that length, that represents that absolute value. So we can now start to make that connection to that process that we have for adding integers. Here's -10 plus -4. I'm going to adjust. I like to adjust the size out here if I can. Maybe it won't let me. Here we go. Now, okay. Well, I will just change the value. To negative. Whoop. Okay. Well, there we go. Little operator error there. There it is. Again, think about that absolute value. Now, same thing here. You get the idea. I'd have -13 plus 6. Again, now we can look at those. Oop, I got it all mixed up. There we go. If I could read. There we go. -13. And then plus the 6. And again, now if I adjust that, now I can start to make that connection, start to develop that process that we go through when we add integers. Now, what does that look like with the other model, two-color counters? Let me take a quick look. Oh, let me put the share code in the chat. And I'll put it up here in the share code box. Now, how can we use two-color counters to model integer addition? Actually, this is addition and subtraction. So I can model. Here we go. I've modeled that first addend of 4, and to that, I'm going to add a -3. So there's my -3. And then now I can do what we call make those zero pairs. Remember, we said one of those concepts when dealing with these models or dealing with integers is that idea of opposites. Now it automatically, whoops, and let me get this one out of here. And now I get a sum of +1. What about 4 minus 6? Now I look down here. Do I have 4 to take away? Or I'm sorry, 4. Do I have 6? Do I have 6 to take away? No, I don't. So I'm going to add those zero pairs. And those zero pairs, with their sum being 0, they're not changing the value because we know that anything plus 0 is that anything. So it's not changing that value, but I do need to break these so that now I can take away my 6, and I'm not going to take it away just yet. I'm going to move that up here because I want to go over to this one over here, 4 plus -6. Now I'm going to add -6. I get my zero pairs. I get my zero pairs there. Okay. Now, if we can then begin to have those conversations about that definition of subtraction to have a vertical number. Valerie, there is a way to get a vertical number line. I know this is one of our improvements that we have been talking about. But if I take this number line from the tool bin,
It's in the instructional
it's in,
tools.
yeah,
Yep.
yep. Wrong tool bin. This one here. Let me get rid of this one. Now I can rotate it. That's a great question, and then I can also drag. So I can make that connection to thermometer. How did I get to the plus or minus two-color counters? Whoops. If I go to two-color counters, I go down here to workspaces and select integer chips. And there we have them. And we can see I can change colors as well. Quick question, one with context. Here's one. This pretty much comes right from the standards. I think the Common Core Standards mentioned something here about um, atom charges. Now, it's been a long time since I've done chemistry, so I can't guarantee that these are actually atoms. um, but here's one with some context, right? Atoms have negatively charged electrons, positively charged protons, and I won't read it to you, but you can read it. So now here we get an opportunity to bring in some science, and now kids can determine what the charge is of these atoms. Again, kind of using that thinking of, okay, well, what's the magnitude? How many negative charges do we have? How many positive charges do I have? And then they can make that selection. Oop, did I forget to put that in the chat? Thank you, Kara. All right, multiplication is, I'm going to put this in the chat. Multiplication can be a little different animal, and I'm keeping an eye on the time because I really want to get to algebra tiles because I have a feeling that folks really want to get to algebra tiles. So I'm gonna go through this example quickly. I can model multiplication of integers with two color counters, right? If I had 2 times 3, think about what that means. What have kids learned by the time they get to us in middle school about what multiplication means? Notice I've got an array tool over here. This means what? Two groups of 3. So I can take a look at that and I can say, oh, thank you, Vanessa. So I can model that 2 groups of 3, knowing what kids know from elementary school, and then 2 times -3. Well, I'm going to copy this, bring that down. Whoops. That's 2 groups of -3. But now what happens when that first, what happens if I have something like -3 times 2? Think about what they already know. What do they already know? There's something they've learned in elementary school. Commutative property. Yeah, thank you, Jacqueline. Right? They've got that commutative property. So, and I'm doing this part for a reason. So now, what if I have a negative times a negative, right? And what is that? How do I interpret that? What does that mean? I've seen it done a couple of ways. I was doing a training a couple of weeks ago, and someone said, "Oh, it's the opposite of 2 times -3." And yeah, it is for us as abstract thinkers. That certainly makes sense. But one of the ways I've seen it is to think of this as removing or taking the opposite of 2 sets. Yep, opposite of an opposite of -3. All right. Well, I don't have -3 to remove. So now I'm going to start at 0. I'm going to make those 2 pairs of -3. I'm going to break that. And now if I remove the opposite of 2 sets of -3, I remove those. For me, that's a little contrived, and I think it requires kids to already do a little bit of algebraic manipulation to say, well, it's the same as 2 times -3. So one of the ways that I might think about that and think about, how we're using those standards for mathematical practice, and we want kids to think like mathematicians and ask questions. And I might look at it differently and ask the question, using what I know about the rules of proof and if-then statements or conditional statements, biconditional statements. What if if a negative times a negative were not a positive? Let's take a look at an example. Negative 1 times, well, negative 1 plus 1 on the left-hand side. If I expand that, I get negative 1 times negative 1 plus negative 1 times 1. Simplifying on the left-hand side, I added an inverse. I know their sum is 0. Over here, remember, negative 1 times negative 1 is not positive, so it must be a negative. This one we have already established. So then I get this statement that says 0 is equal to negative 2, which doesn't make any sense. So therefore, a negative times a negative might be a positive. Now, I'm not saying that these two different models aren't good for for multiplication of, whoops, why does it keep doing that? Multiplication of a negative times a negative. I'm just saying that, based on what I've seen, what I've done in the past, it's a little bit of a contrived use of the manipulatives. All right. Let's see. Now, I want to take a look at division. I'm trying to keep up with the chat. Thank you. Let's take a look at division. Oops. And I'm going to put this in the chat for everyone. All right. So how can we represent dividing integers? Well, a negative times divided by a positive, that's not so bad, right? I can think of that at how many negative counters in my two groups. Well, I can make two groups. I'm just going to, whoops, if I could highlight the right ones, bring that over, right? Or if it's a negative divided by a negative, in this case, negative 8 divided by 2, I'm sorry, negative 8 divided by negative 2. Well, I could think of that at how many sets of negative 2 are there in 8, right? But when does it get a little dicey? Well, when we have a positive divided by a negative. One way is we could think about that in terms of multiplication, right? So what I'm going to do is I'm going to take you to our task page, grade 7. We've got a task called Can You Relate? When I click on this, I get the teacher notes, and in those teacher notes is a share code, and I can take that share code. And now I put that share code in there. And now we've got a quick task on, hey, let's use the counters, let's review the results for multiplying, and then use that to complete this grid using the two color counters. Oh, thank you, Kara. Using the two color counters to show, to complete that grid to show the rules for multiplication and division of integers. Question came up, how did I get to the tasks? All right. So I went, let me start here. I'm on our website. Go up here to resources and click on tasks, and you can see now I can filter them by grade or domain, and that's how I can find them. So I hope that answered your question. All right. I am going to go to back to my Brainingcamp. Do you make words seen and unseen? So here in our tools, we have this. I think this is what the question is about. Discover tool. So let's say I wanted to, let's cover this grid. I can bring it out there. I can adjust it. I can lock it so students can't move it. And now I can reveal that. So it's a tool that's in the tool bin over there. All right. I'm taking a look at the time because I really want to get to um, algebra tiles. But before we do that, I want to take a look at a task through with color tiles because I think for me one of the things that manipulatives really are really beneficial is helping kids see patterns, develop patterns, build the patterns, and then help make those generalizations. So here we can see we're using color tiles. We've got some growing pattern down there at the end. So how might you describe that growing pattern? Again, coming back to that visual, that's the contextual, the verbal representations. We can ask kids to describe that pattern, put it in their own words, describe what they see, what's happening. Looks like I'm starting out with one, and then I'm adding one on top and one to the side, and I'm continuing that pattern. And so then I might ask some further questions of what might be in how many tiles in figure 10, in figure 50. Well, I don't expect them to build that many different figures, right? So we can use what they've built to make some of those generalizations, right? And to begin to look at filling out this table. So let's see, figure number 1, 2, let's see. So how many tiles? And then I could enter text here, but I'm just gonna use my pen. And now I might, okay, how many tiles were added for figure 1? Well, I had to add the 1. How many now did I add for figure number 2? We can start to make those observations. Oh, figure number 3, how many did I add? And so forth. And now they can go and they can build those, begin to build those different figures or those different terms. And now they can start to make those generalizations about how many tiles, what was the number of tiles added. And if my memory serves me right, I think it's 2n minus 1. And how do we determine what's the perimeter, right? And so forth. So we can really get kids involved engaged in doing that building of those figures or those terms, and then from there using that, collecting that data to look for those patterns, make those generalizations, and start to connect some of those multiple representations. All right, I'm keeping an eye on time. I'm 2 minutes behind schedule, so I want to go to algebra tiles because those are they're one of my favorite. How many of you are familiar with algebra tiles or curious about algebra tiles? I think it's one of the more useful. Um, curious. All right, one of the more useful manipulatives. So I'm going to click in algebra tiles and do a quick walk around here. Um, you can see over here we've got those in the left-hand side in that tool bin. We've got our algebra tiles. And let's see, we've got multiple workspaces down over here in the right. I've got one for solving, and we'll take a look at using that in a little bit. And then we've got another workspace called factors. All right, Tevin loves algebra tiles just like I do. Awesome, awesome. All right, let's go back to the basic workspace. Let's figure out what these tiles represent. So I'm going to bring out this 1. And I am going to, let's see, turn off my workspace label, and I'm going to turn off my object labels as well. So we could all identify this square, this shape, right? This is a square. And let's come to some agreement, right? Let's say that this square has a length of 1, but we know that if it's a square, all the sides are the same length. We're going to say it has a length of 1. Now, algebra tiles are an area model based. There's rectangles based on area. So if I know that this yellow is 1, now what does this green bar or rectangle represent? Well, I know that. I know that this distance is 1, that length is 1, and I know you're going to have kids that are going to say, okay, well, if this is 1 here, well, this is, let's see, I'm going to put these here, and I'm going to come up and say, well, it looks like it's about 4. Well, and your kids will do this, and my students did this, and then we finally said, well, it's not exactly 4. We don't exactly know what it is. What do we call in something in mathematics that we don't know what it is? Well, we're going to call it X. And then we can talk about, we've got the additive inverses, and those are the red ones. We've got -1. We've got the opposite of X. We've got X squared, and we've got the opposite of X squared. What I like about algebra tiles now, since it's an area-based model, I'm going to invert this one. What I like about it is I'm sure many of you probably have students who confuse or want to say that 2x and x squared are like terms. They see the 2, they don't think about, oh, that's an exponent. Now I can give them a geometric model that shows, well, these are not like terms because they're not the same shape. Okay? So that's what I like about, one of the things I like about algebra tiles is being able to identify and establish what those pieces represent. We can also, if I go down here and click on the Y tiles, I also get the Y representations. And now once I have these, I know what each of them are, I could do some really kind of fun things, right? I could go here and I could start talking about the perimeter of this shape. What is this? This is 2. I should use the bracket we have. I know my colleagues are saying that 2. And what's this distance here? That would be x minus 2, and this would be x. So we could do some kind of fun things with the algebra tiles, even using that geometric relationship that exists between them. Now I'm going to go back to my PowerPoint real quick because I want us all to try something. Oops. All right. Little number trick. So I'm going to ask you to rational coefficients with variables. Jennifer, no, there is not at this point. The thing about algebra tiles is working with integers. Then once you get that process and that algebraic reasoning down and comfortable with that process, then you can go to rational numbers. There is a way to do it, but it's a little contrived. And you can email me. You'll get my email at the end, and I can show that to you. So I want everybody just to try a quick number trick. So take a number, increase it by 4, double that, find 4 less than what you did in number 3. Sorry, those numbers are so small I couldn't figure out on how to enlarge them. Split it in half. Subtract your original number. And what did you get? 2. I see 2. I see 2 a couple times. All right. Whew. All right. Well, I want to take a look at using algebra tiles to do something that's kind of fun like that. And here I'll put the share code in the chat. Same trick, same number trick. Now I think there's a couple of them. Yes, thank you, Vanessa. Let the number be X, right? So we can now start to go through, okay. And then we can also make get to that symbolic representation. All right, I'm gonna bring a text box out here. I'm not going to do this whole thing because this is a bright group, and I'm pretty certain you're grasping all this, right? How could I increase that by 4? I'm going to take this, I'm going to copy it, and now we can go and I can take this and oh, there we go. I've got x plus 4. So again, I wanted to think of like a, kind of a unique way to engage middle schoolers using these, what we called them in my classroom was the sense making devices. Um, the Google folder, I'm going to put the link in the chat once again. Oh, thank you, Kara. All right. So that's one example. When you get into that Google folder, you'll see that there is another example of a number trick. Feel free to use those, take those, and use them as you see fit. I always like to provide something that you can use right away, make your own. Let's see. Let's see. Another to quickly take a look at using algebra tiles to solve an equation. We'll go through this one fairly quickly. And it looks like I have 3x plus 5 equals 11, 9, 10, 11. All right. Now, what I'm going to do is I'm going to take all this and I'm going to copy it because I want to keep my original because I want to see that process as I go through it. And then I'm going to click down right here in this zoom to fit button so it brings it all back on the screen so I can see it. Let's see. So let's go with, I'm going to copy this. I'm going to invert it. What I do to one side, got to do over here, right? And then I can I can simplify, find my 0 pairs. You'll notice over here that even though I grab more, there's not a one-to-one correspondence. The system's going to say, oops, look, you did it. You've got your 0 pairs. Now, notice when I hover over this mat, let me just move this over a little bit. It turns blue. That tells me I can interact with it. So now what do I have here? I'm going to go here, click on there, and I'm going to turn the label on. I have 3x equals 6, but I want to solve for 1x, right? So to represent or to model that division by the coefficient, I'm going to add rows. So now I can use my fair share meaning of division. And I find that x equals 2. I do it that way because the other way I've seen it is, just to delete these, but you're not really deleting them when you do the algebraic process, right? You're simplifying. So there are other equations there that you can play around with. I'm looking at the time because I want to get to I want to go to the factor workspace. All right. Factor workspace, again, you'll notice here when I hover over it, turns blue, so it tells me I can interact with it. I can change the size, and I'm going to copy it. And let's see, let's make a quick factor. Let's factor this 2 ways. Now, have they seen this area model before? Have they seen the area model before? Yes, I agree, Alyssa. It's not cancel, right? They're not canceling. Oops, so now I got to copy this, get those, oops, get those 3 here. All right, so there's there's my, oops, I accidentally locked it. Uh, so there's my product. I'm going to copy it, bring it over here. And this is where, for us as abstract thinkers, like we didn't learn this way. So sometimes I'm going to say the manipulatives can kind of get in the way a little bit. So we really have to kind of put down or put away what we already know about mathematics or about how we would have done this and when we learned. Um, so really, it's about making that rectangle, right? That what I'm going to call that product rectangle. And here might be one way. We'll do it the one of the quick. We'll do it the quick way. I can make that rectangle. Notice how all the dimensions are matching, right? I'm making a rectangle. If I couldn't make a rectangle, think about early on in multiplication. But if I couldn't make a rectangle, then what kind of number would it be? In this case, it's wouldn't be factorable over the real numbers, right? Now we can place our factors here. And now I'm going to click on the frame and turn my labels on. And now I can see one way that I factored it. Yes, they did do it with base 10 materials. Yes. Think of that coherence. Yes. I love it, Marilyn. Um, they've done this. They've seen this area model, right? So I will leave it up to you what the other way to factor it might look like, right? Could be, as long as it makes a rectangle, right? As long as we get that rectangle, we're going to be okay. Um, let's see. I'm going to go back briefly to my PowerPoint because Marilyn pointed out to us that they've seen this area model, the use of the area model before. So if we can really, and this is why I looked at that, 2 times 3 and then 2 times -3 and -2 times 3, right? Because rather than, you know, putting them through maybe some arduous processes, let's go back on what they already know. That's where research tells us is that that's when really deep conceptual understanding, if we can connect other or previously learned concepts to new things, our understanding is that much stronger. So they've seen that area model before. You'll notice here, what do you notice in these two images here? How are they alike? How are they similar? Or how are they different? Here's my 10. There's my 4. Here's my x plus 4, right? Same partial products, same area model. Just, I don't know, for me, it's like just connecting to what they've learned earlier just is very, very powerful. All right, I apologize for going fast, but I know I wanted to be respectful of everyone's time. Can you change the color of the base 10 blocks? Yes, you can, Marilyn, and I can show you in a second. Reminds me of an ancient saying: I hear and I forget, I see and I remember, and I do and I understand. That's what what my students had to the change they kind of went through, that they had to go through. By involving them, they now became more owners of their learning. They were more engaged in their learning. They owned it, right? And when you talk about seeing light bulbs go on, um, when kids are working with manipulatives and they see that, oh wow, what they just built and how that relates to the concept, um, you'll see those aha moments. I've been with teachers who have seen that aha moment. Yep, they can turn them into integers and use multiplication, division as well. Absolutely. Absolutely. Connecting to what they already know. All right. So, middle school teachers or really any of us who are just getting used to using manipulatives, do it one at a time. Do one manipulative at a time, right? It it's it's a lot to do. Oh, look at this one too, and introduce more than just one. Take it slow, one at a time. Make sure you have some exploration time, not just for your students, but for you as well. Um, we were going to look at Cuisinart rods tonight. That's one that for me, like you really, really have to spend time getting to know the relationships between those rods before you can really do any meaningful tasks with them. So make sure you work in some exploration time. It'll be time well spent. Make them available. Now, today with virtual manipulative, that's fairly easy. um, but remember that they're they're purposeful tools versus playthings, right? They are tools that we can use for learning when we use them with integrity. Excuse me. And please feel free to check out our resources. Again, up here, excuse me, up here I click resources. Not only do we have these tasks that are grades K through 8, but we also have, oh, thank you, Kara. We also have, these are new, some ideas videos, because we wanted to give folks a start for working with manipulatives. So here's one. Well, I'm going to go to grade 6 because this was middle school focused. And we'll go up here. Understanding, and this is squeezing air rods, understanding equivalent ratios. Quick video. It's probably less than 30 seconds, but then we also give you the share code. I can copy that. And now take that share code, put it in that share code box, and you've got something that you can start with. You've got something you can start with. You can watch the video. The videos, I don't think any of them are more than 45 seconds. Yes, you can just quickly to answer the one question. You can change the the color of the base 10 blocks. If you go down here where it says in this the settings down here where it says multicolored, if I click on that, that'll change them to all one color. So I can't individually change. I can change them to all be one color blue or get multicolor where each place value is a different color.